where am I at? Effect size. So we talked about like saying, is it significant? We want to say, all right, if it is significant, we can't actually say how much of effect it is. So this is actually a really subtle point, is that our t-tests, our high statistical tests, they only say, is this significant? So if you get a big, for example, if your p-value is very, 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 very small, you're like, oh, like cool, like it's significant and it's such a small p-value. That means it must be a huge effect. It's not necessarily true. It just says that it's definitely, there is an effect, but how much that effect actually is, that's different. So for example, if you get like 200,000 Snicker bars, okay, I must be hungry, but 200 Snickers bars, right? 200,000 Snicker bars, and you find the mean is, like 118, right? And you use your t-statistic and it's supposed to be 120, and you're like, whoa, like the p-value is super, super small, right? It doesn't mean that there's a huge change in the actual, like in a huge effect in that sense. It's just saying, oh, there is an effect for sure. However, if you have, let's just say like 10 Snicker bars, right? And you find out that the average is like 80, right? 80 grams versus 120, like, like 2/3 of like what it should be. You might not actually find that is significant, right? But that's partly because you probably didn't have a large enough sample size. But there might actually be a strong effect there. So this is where like it's a subtle difference. So this is where we can actually use effect size to say, well, how much of an effect this is. And so this is really useful in meta-analyses because it allows you to compare multiple studies to say, okay, we can see all these studies that show there's a significant difference, but how much does that difference actually matter? So you actually see this a lot in the medical field. They'll say, oh, there's a statistically significant difference in doing this thing, but they don't talk about what the effect size is. So I think one example of this is, it's a little common misbelief. I can't remember exactly the numbers. I'm going to misquote it, but I'm say it about, is that they talk about women having children after like 35 or something like that. I can't remember the exact age. And they're like, oh, like, there's a higher chance of, there's like double the chance of having a child with Down syndrome, right? Well, that double the chance goes from something like 0.02 to 0.04. And it's like, well, percent. And it's like, that's like almost nothing. It's like, technically it is a significant difference, but in reality, it's not significant where it would make sense to actually recommend to someone, say, well, okay, like you're a higher chance of, this thing, so we should do something about it. Okay, and this is where the effect size really matters. Another aspect of this kind of fun thing is coffee. Coffee gets a really bad rap for some or whatever reason. So one thing they talk about with coffee is like, oh, there is technically a higher, there's a correlation. Whereas actually interesting, there's a lot more positive things. There are things like, for example, drinking more coffee can actually help your heart. But the effect size of this is relatively small. So even if there isn't an effect, it's so small, basically insignificant. Basically comes down to the fact that you're probably fine drinking coffee, unless you have a very specific health problem. But that usually hasn't been found. Anyway, meta-analyses, that's where we use this part a lot. So kind of going a little bit is, I'm going to warn you guys, so a little bit more mathematics, but we'll kind of walk you through this, right? So our first thing basically is like, okay, like how different is this? So you can essentially compare like two different populations and say, okay, are these different populations same? And this is actually directly taken from the curriculum where they compare males and females, I think, with height. And so basically what we can calculate is this using this equation right here, which is basically that sigma 1 and the mu 1 basically representing one population and 2 representing another population. And so remember that sigma represents our standard deviation, our mu represents our mean. And basically we say, okay, we have a crossover between these parts. And what this is really trying to say is essentially how much does this overlap? And this is really what's going on here. So if you have a larger mean, for example, you would have a bigger overlap. Or I'm sorry, if you have a larger standard deviation, your distribution is going to be much wider and it's going to cover a larger period, right? So you can kind of see if I drew this out, I don't want purple, that's actually probably the worst color I can draw. If I have something like, let's say the distribution looks kind of like this instead, it's much wider, okay? There's going to be more crossover in this case. And that's because our sigma, let's say sigma 2, okay, our standard deviation is actually larger. So basically what happens is that this crossover, this sigma 2 will go up times the mean, and this sigma will go up here. So if basically what happens is that it's going to increase that size more than it's going to increase that crossover if that mu stays the same. If that average goes down, right, or average is smaller and smaller and smaller, right, is that there's going to be less and less of an overlap in that case from that difference. So this is where like there's a trade-off between the two. So you can kind of see here is that if this is closer, like where we change the mu to be very different. And you can see here that there's a huge, in this case, there's a huge effect size versus this over here. It's not very much difference between the two, okay? And it's just a way we can calculate it with a number itself. All right, and this kind of brings us a little bit of probability of superiority. It's kind of mentioned a little bit quickly in the curriculum, but I'll just kind of mention it here. It's basically what you do is you basically say, what's the probability of a randomly picked member from group number 1 going to be different from a random member from a group number 2. So you can actually just basically compare all the members of the different groups and see what the probability of them actually being different from each other. So the curriculum kind of shows a little bit of how you would do this. Okay, so that's another way you could kind of represent this. And our last one is our Cohen's d, which is a parametric way to check out effect size. And so here is basically, I'm going to just straight up say, don't stress out about these equations. This is more like how you would essentially, what's going in the back end. But basically what happens, you'll see this sigma pooled, which is basically what we have here. What's nice about Cohen's d is that it considers larger populations. If their population is larger, then maybe there's a bigger effect size. Question? Is there a question? No? Okay. So basically, Cohen's d allows us as another statistic. It's another thing for us to measure against. So just kind of know is that like this value, it's like there isn't a specific number that you're looking for, this d right here. And essentially what you're kind of looking at is like how different are these means. And this is why we kind of see like how many standard deviations, which is really standard deviations pooled, what this looks like. So a general rule of thumb is that a small effect is like 0.02, a medium effect is 0.05, and a large effect is 0.08. So we can actually show this a little bit in this part with some code, okay? So this actually comes again from the curriculum. I'm trying to not make anything new, so that way when you guys come across it again, you can just reuse it. But basically, we're getting specifically from SciPy, the stats package. That's where we can use these tools. We're basically taking in a probability density function, and we say, okay, from this probability density function, from this sample, we say, okay, get the mean, get the average of this random variable. We use NumPy basically to create a linear space to go from the mean to another standard deviation. So this is coming directly from this part right here. Okay, and so essentially what we're doing is like, okay, like let's see how far away from we can get from standard deviation, and then we can actually calculate the peak of this normal. So I'm going through this pretty quickly, but just know that this curriculum does go through a little bit closer. We have the overlap of superiority, and then the plot of the PDF itself. So this is for us to visualize it. So this is just mostly to show you like what a Cohen's d. So this, for the most part, you're not gonna have to worry about necessarily like calculating, but I want to show like what this looks like for a Cohen's 0.02. So we can see a Cohen's of 0.02 is that basically a very, very small effect. You can see there, those two samples, that pink and that blue, are very, very close together. Basically, there's almost like no difference between the two. Where we have a Cohen's d of like 1, okay, you can see there's a much larger effect, okay? And you can see there's definitely an effect in here. And of course, you can go even further in this case. You can see like 4.0. We can see that there's a huge effect going on here. So this metric, this d, allows us to kind of like quantify saying, okay, how much of an effect do we actually care about, okay? And again, what an effect do you actually care about? If you are talking about, you know, obviously if you have a very big effect, this is a huge difference. If you know, this might be kind of like, okay, like this is what we're looking for, like some effect. This might be a small effect for some situations, but if let's say I'm trying to think of something like on extreme ends, like, okay, like this can either like, you either do nothing and you die, or you do a little bit of something and you live. It's like, well, okay, like if you give this drug, you're like, oh, this has a small effect, but this could mean a huge difference for us. This is where maybe you say, okay, there is a small effect, and then it's worth us, you know, actually taking this far. However, if, for example, let's say this right here is talking about painting the store red versus blue versus green or whatever colors you're looking at. And this is like the number of sales. There's a slight significant, there's a slight effect on painting it blue instead of red. You're like, cool, like that's awesome, but it's going to cost us so much more money to actually paint all of the store blue that it's not worth us doing it, even though there is an actual effect. And this is where technically your p-value might be very, very low in the sense that there's definitely an effect, but that effect size, the amount that it actually changes, is really not that significant and might not be worth your time. Okay. So that's kind of effect size. Cohen's D is probably, I personally like Cohen's D in the sense of like how well it measures. There's other ways you can measure effect size. Statisticians can talk all about this all day about like, what's this number? In the end, it's a number that is guiding your principle. So the important part is not saying, oh, my Cohen's D is 0.073. It's the important part is saying, well, how much of an effect is it? And is it worth, let's say for your business stakeholders, is it worth for them to actually make changes based on that effect? Right. Cool. So any questions in general? Okay. So thumbs up, thumbs down, or at least the concept of this effect size. And hopefully like Cohen's D, you can kind of see what you're really doing is you're measuring that overlap. Okay. Cool. I see some sideways, and that's probably because I think, to be quite honest, I went through this very quickly. I didn't go through the code. I didn't go through, these numbers and stuff like that. And this is where, to be honest, the curriculum does a really good job walking through it. And I would strongly just make sure you kind of walk through the section 20. Again, section 20 is particularly important for the project. So I would make sure you really understand those aspects. Okay. So I'll go ahead and stop sharing my screen here, and I'll go ahead and stop recording.